So we've already kind of had a brief introduction to the within subjects of repeated measures ANOVA. We're going to just basically put what we've already been talking about to slides. And for this particular part of the lecture, we're going to talk about how to hand compute within subjects ANOVA. And again, it is a little more complex, but it's using very similar techniques, but not identical techniques to what we've done in the past. We're still going to be looking at individual scores based on condition, but what we're doing with them is a little different and the equation's a little different. And finally, for the last lecture or last audio set of slides, we'll be talking about post hoc testing and matching with subjects designs. So the within subject design, the test is going to be used when we're comparing two or more conditions or groups. So again, we have an independent variable that's categorical with 3 or more levels. We may be using it when the number of available subjects is simply limited. So we may not have enough participants to actually have a strong or robust design by dividing them into individual conditions. So we may be in a situation where we have no choice but to use a repeated measures design. We can also use this design if we're intentionally looking for overtime comparisons. So for example, if your categorical variable is 1 week of treatment, 2 weeks of treatment, and 4 weeks of treatment, and you're looking for an increased and continuous improvement, that would actually be a design that would be almost tailor-made for within subjects ANOVA to look at that comparison. Again, we can be using this for participants that have been matched on one or more covariates, and I simply want to reiterate once again that if you're using matching, it is methodologically upon you to make a strong methodological and theoretical argument that you have done enough matching to justify using this stronger statistical technique. And finally, you may simply want to reduce error. You may choose the within subjects design not because of a limited number of subjects or that you're making overtime comparisons or that you're using matching. It may be simply that you know that what you're looking for may be a smaller effect and you want to use a design that's more likely to find it if it's there. So the advantages and disadvantages, the big advantage is it increases power by reducing individual differences. Some disadvantages are, especially depending on what you're actually studying, carryover effects can be very problematic. Your participants are going to be exposed to every one of your conditions, which means those conditions may have carryover effects into their additional conditions. So for example, if you're actually looking at a 1 week versus 2 weeks versus 4 weeks of intervention, is it that indeed 2 weeks causes more increase in whatever you're trying to improve than 1 week? Or is it simply that 1 week was enough and you just keep getting better and that's now what you're capturing? So it does create some questions of what are we actually finding. And finally, if you are using that overtime comparison, recognize that you have to be fairly careful, and again, you want to be methodologically and theoretically bound to what is the time differences you're looking at. How much time are you allowing to pass? Because there may be time-related threats to validity. Not only, especially if you're looking at younger populations or older populations that may be having fairly large changes in their developmental abilities over the time of the study, you also have to recognize that there's the potential for history effects. So for example, actually a very good example of this was there was a fairly large federally funded study looking at how children dealt with negative events in their lives in New York City that was an overtime event, an overtime study that was being conducted in New York when 9/11 happened. And basically, I mean, they got some interesting data from that study, but it was no longer the study they were wanting to look at because they were wanting to look at basically overtime developmental changes in children as they grew and developed different opinions about how to react to negative events. But there was such a negative event that so impacted their lives, and many of them experiencing kind of terror and dread to which they had never actually been exposed to before, that they were no longer able to look at what they were interested in looking at. So just recognize that when we do an overtime comparison, there can be a very good reason to do it. We may in fact be that's exactly what we want to look at, but we are opening ourselves up to potential threats that could occur within that study that would be much less likely to impact a study that happens over a very short period of time. So again, we've already kind of talked about the variance in the within subjects ANOVA. It does not measure or estimate individual differences since the statistics assume there are no differences between the groups. So again, when we're looking at repeated measures ANOVA, we have that top equation, the between treatment, the effect, individual difference and error, divided by individual difference and experimental error. And a lot of times, the individual differences is one of the larger numbers that's in this equation. The difference in the equations are attributed to the treatment effect or experimental error is all that we're looking at. So again, we have between treatment and change difference and experimental error divided by change difference and experimental error. And change difference is not necessarily treatment size. It simply represents kind of how people are changing from condition to condition individually and not as far as the group mean. So the between treatments number is still group means. The change difference is not quite the same as all individual difference, but it is looking at how individuals differed from group to group. So again, computing the within subjects ANOVA, once we actually have our sums of squares between an error, it's the exact same equation that we use with a repeated or an individual or between subjects design. So again, the top of the equation is sums of squares between divided by degrees of freedom between. The bottom of the equation is sums of squares error divided by degrees of free error. And we already kind of talked about that what we're looking at here is a little bit different. So what is on the top of that equation, how we calculate the sums of squares between, is actually the calculation of, again, what we have to calculate is the mean differences, but also the change differences. So our equation in this case is actually the sum of a squared divided by small n, the number of participants in one condition, minus T2, which is representing that change difference, divided by the total n. In other words, how many total slots were there? You have 3 conditions with 5 people in each condition. That's 15 conditions, 15 individual scores. That's large n. And again, it's going to be divided by the degrees of freedom between, which in this case is k minus 1. So that's the equation we're going to need to work with if we're wanting to run a hand calculation of the within subjects ANOVA. So let's take a look at the in total of this equation. We have, again, that effect size and we have that change difference, but at the bottom of the equation, we also need to add in error. So this is the equation for the bottom of the equation. We have y squared minus, again, the sum of a squared divided by n, minus the sums of squares divided by k, plus, again, that change difference divided by the degrees of free error. And again, degrees of free error in this case is the number of conditions, k minus 1, multiplied by small n, how many people you have experiencing all these conditions, minus 1. Now notice that 2 parts of this equation we already calculated for the top of the equation. So again, this is actually a fairly simple equation to work with as well. So now we're going to walk through it. We're going to first calculate the top of the equation, which is these 2 numbers. We're going to calculate the sum of a squared divided by small n and t squared divided by large n. So before we do that, though, of course, we have to formulate our hypotheses, our null and alternative hypotheses, and select an alpha. And again, in this case, the alpha is almost always exclusively going to be selected as 0.05 or lower. So our null hypothesis in this case is that there is no difference between students at time 1, time 2, and time 3. That graduate students drink just as much coffee in graduate school as they did before graduate school. Our alternative hypothesis is there's at least one difference between the means, that students' coffee consumption has changed since entering graduate school. So we need to calculate our critical degrees of freedom. In other words, what is the number that our test is going to have to come out as a value or higher for us to claim a P of 0.05 or less? So again, we need our degrees of freedom. In this case, we have 3 potential times that we're measuring graduate students' coffee drinking. So our K is 3. 3 minus 1 is 2. So our degrees of freedom between is 2. How many participants we have? Well, in this case, we actually have 6 total participants. So k minus 1, 3 minus 1 is 2. And then n minus 3, in this case, is going to be 5. So 2 times 5 becomes a 10. So the bottom of our equation, the degrees of freedom error for it is 10. So what we need to find out is what is the critical value for an alpha of 0.05 with a degrees of freedom between of 2 and a degrees of freedom between, or error of 10. In this case, we find out it's 4.10, and we do that by looking at one of those wonderful charts in one of our books. In this case, again, we're going to find our degrees of freedom for the numerator and the degrees of freedom for our denominator. So 2 by 10. And for a p-value of 0.05, we see that 4.10. Now, if we actually found that our test statistic was above 7.56, we could actually report that it was a p-value of less than 0.01. So we're going to get our actual data. In this case, we have our baseline, so how much coffee they drink before graduate school. We have their spring drinking, and we have their summer drinking. So this is how many cups of coffee they're having every morning. So we notice, for example, that before Chris ever got to grad school, she drank 5 cups in the morning. And her spring semester, she drank 7, and in her summer semester, she drank 10. That's quite a lot of coffee. So the first thing we need to do is calculate A. A is simply the sum of the actual individual scores at each time. So A1 is for the baseline. It's 2 plus 3 plus 5 plus 0 plus 1 plus 1. It's that second column. Our A of 1 is 12. Our A for the second group is 3, 5, 7, 2, 2, 1. In this case, it's 20. And finally, for summer, our A is 3, 7, 10, 5, 4, 0, 29. We now have the A for our first time, the A for our second time, and the A for our third time. Now, to calculate T, we're simply adding up the total scores the person had across all 3 times. So Daniel had a 2 at baseline, a 3 at spring, and a 3 at summer. It's that second row. We add those together. 3 plus 3 plus 2 is 8. That's Daniel's total across all 3 conditions number of coffee drinking. And again, going a couple down to Chris again, we had 5, 7, and 10. That's a 22. Once we have each one's total in this final column to the far right, we add those all together. 8 plus 15 plus 22 plus 7 plus 7 plus 2. That equals a T of 61. So we now have our T, 61, and we have our 3 A's, 12, 20, and 29. Taking these numbers, we're going to go back to that equation. So the equation was the sum of A squared. So we're going to take our 3 A's, 12, 20, and 29, and we're going to square them. 12 times 12, 20 times 20, 29 times 29, and we're going to sum it. We're going to add them together. And then we're going to divide by small n. There was 6 total people in our study. We're going to subtract, however, T2. T was 61, square it, 61 times 61, divided by big N, the total number of scores that we had in our data set. In this case, 18. And then finally, we're going to divide that number by the degrees of freedom, in this case, 2. So at this point, we're just going to run those numbers. And what we end up with is 1,385 divided by 6 minus 3,721 divided by 18. And then we're going to divide both by 2. And again, we're just going to walk through that equation and get to our number. So we now have the number for the top of the equation. We're now going to look at the rest of the information that we need to finish the bottom of the equation. So we already have our A's, we already have our T. We now need to calculate the mean of each group. So we have a mean of 2.0 for the first one, and all we're doing here is we're taking A divided by 6, the number of participants. We have the mean for spring. Again, A is 20 divided by 6 is 3.33. And we have the mean for summer. A is 29. 29 divided by 6 is 4.83. So we have those numbers. We now also need to get y squared. Y squared is simply their scores squared. So we're going to take each individual person's score and square it. So baseline Daniel at 2 is a 4. Baseline Travis at 3 is a 9. Baseline Chris is 5, which is a 25. As we square each of these numbers, we're then going to sum them up. So the sum of y squared for baseline is 40. The sum of y squared baseline for spring is a 92. And the sum of y squared for summer is a 199. Once again, we're going to take these numbers back to our bottom equation. So going to the bottom of the equation, we have the sum of y squared. So we're going to take those 3 y's and simply add them together. It equals 331. We're going to take the a squared divided by small n from the top of the equation, 1385 divided by 6, and just put it into this equation. And we're going to put the t at the end of the equation, t squared divided by big N, 3,721 divided by 18, and just pop that in the equation as well. What we're adding, though, is the sums of squares. 8 squared, 15 squared, 22 squared, 7 squared, 7 squared, and 2 squared divided by the number of conditions, k, 3. And finally, the entirety of it divided by the degrees of freedom of error, in this case, k minus 1 times n minus 1, and that's small n, which is a 10. So again, we're going to simply run through the equation. So what we get now is the calculation of the mean squares between groups, which was 12.06. We have the computation of the means of squares within groups, error of 1.52. So 12.06 divided by 1.52 equals 7.93. That is our calculated F statistic. We now compare the results to the critical F. The critical F for a 2 degrees of freedom in the denominator and a 10 degrees of freedom in the denominator was an alpha for 0.05 was 4.10. Our obtained F statistic is actually 7.93. We reject the null hypothesis. Students' coffee consumption has changed since entering grad school. F equals 2, 10 equals 7.93 with a p less than 0.05.